So talking about quarks, and Pete was asking about if you try and pull quarks apart, you just get more quarks. Well, yes and no, because the thing is, there's a history. A lot of bullshit talked about quarks and about strong interaction stuff. The thing about the quarks is the quarks are originally seen as and quarks are a symmetry themselves. So the original reason for inventing these particle things, Murray Gell-Mann, and a lot of people found this horrible at the time, postulated that that you could get this stuff. I'm just saying that where quarks came from was originally from an observation. When you started getting up from things like the proton and the neutron up to the cascade particle, up to the sigmas and chi's and cascade particles, there are a whole group of particles here that consist of up and down quarks in the standard model. And there's a very nice symmetry that came from postulating the existence of these fundamental building blocks called quarks. Then when deep inelastic lepton scattering came along, first of all with electron scattering at SLAC, and secondly with my experiment at CERN with deep inelastic muon scattering at the European Muon collaboration, you began to be able to probe inside the proton and have a look at the scattering off what was inside the proton. So at low energies, what you see is a whole proton. The thing just operates as a unit. If you go to the sort of higher energies, you begin to see structure inside the proton. These things are described by things called the proton structure functions. You go to a bit higher energy, you begin to see you're bouncing off things as though there are hard bits inside the proton. And it's at that point that you began to see this, that people proposed something called the quark parton model. So the idea here was that the quarks were not just a symmetry, but they were sort of represented by real particles inside the proton. The proton was composed, it was thought of an up and a down quark, really. And at first there seemed to be some fairly good evidence for this. You saw scattering off. If you're doing scattering off a proton, you could work out, proton has a certain mass of the proton. And if you scatter off something by looking at if you bounce an electron off a proton, by looking at how hard it bounced, how hard it recoiled, you can transfer that into the center of mass frame and see how much mass it hit. Now you might think at low energies, it's the whole mass of the proton. At higher energies, it's very seldom that. It only interacts with a fraction, always less than a half of the mass of the proton, but usually less than a sixth, usually less than a thousandth if you go to very high energies. So you're only hitting a bit of the proton. You're hitting something that's a part of the proton. Now, at the first energies, you tended to hit quite big bits. So you had scattering that hit fairly large bits. Now, when you're scattering, there's a couple of variables that you measure. One of them is how much mass of the proton did you hit, which you can calculate from the kinematics. It's called X. So Bjorken X. So that can go from 0 to 1. 0, you didn't hit it at all. 1, you hit the whole thing. So another thing is called Q squared. That's the full momentum transfer squared. Q squared is how much energy was in the photon that in quantum electrodynamics was responsible for the interaction. So in comes an electron or a muon. It bounces off in some direction. From that angle, you can calculate how much mass energy was in the photon that it hit the proton with in quantum electrodynamics. That tells you how much energy you hit it with. Now that thing has a certain wavelength, which you can work out. So that tells you how much you resolved it by, how hard you looked. So you've got these two dimensions. One dimension is how much did you hit? And the other is how hard did you hit it? X and Q squared, right? So what you measure, and this has been what people have been measuring since I did my PhD on this back in the 80s. What you measure is that most of the scattering is at quite low X. So the vast majority of your things you hit only hit a tiny fraction, less than 10%, often less than 1% of the proton mass. So you're hitting stuff inside the proton that isn't carrying much of the proton mass most of the time. Now, you can do a cut on X, so you just look at stuff where you look at, let's say, a third of the proton mass or a sixth of the proton mass. And then you might hope that's hitting the actual hard bits inside the proton. Now, why do we think there are hard bits inside the proton? Well, that comes about because if you look at the relationship between, you look at the relationship as a function of these variables that I've talked about. So you look at terms of x and q squared. If you look in terms of q squared, a characteristic of point scattering, is that it doesn't matter what q squared you hit it with, because you're not resolving how big it is. It doesn't matter how hard you hit it, because if it's sufficiently small, how hard you hit it won't modify the probability of you hitting it. So, and that's called a scaling rule. And in the graphs of F2, the nucleon structure function, that comes out as just being a flat line in the graph. It just shows scaling. Now, if you look at those F2 structure functions, I wonder if I can put one up. Just a moment, I might be able to put one up. I'll see if I've got one in this talk. Just a moment, might have. Oh yeah, here they are. I'll show you them. Here we go. Right, so I'm going to share screens, gentlemen. This time I'll try and remember to actually share the screen, all right? Can you stop sharing, Arnie? Or you have stopped sharing? You're too quick for me, young man. That doesn't happen very often. Good. Right. Okay, I'm presenting. I'll just go to an example. There we are. These are structure functions. Now look. Q squared's along the bottom axis, and this is a later plot than I did, but it's the same sort of thing. So Q squared's along the bottom axis. Can everyone see that? Okay, Q squared's along the bottom axis. So if the lines are flat, which they are pretty much, look, they're pretty much all flat. This is point-like scattering. These are at high values of x, look. Higher values of x. So when you lower values of x, it begins to get different, and q squared matters. So this scaling behavior is the evidence for point-like structures within the proton. That's what it is. But I'm saying point-like and not point. The thing is that scattering with point. I mean, if a thing was truly a mathematical point, you'd always miss it, right? Because it's just almost not there at all. So there's something called a cross section, which is the likelihood of you hitting it. Then there's this behavior here, which is the kind of, so where is it actually flat? It's kind of here at Bjorken x of 0. About a sixth, roughly. It's fairly flat, 6 down to 20th. It begins to deviate. So what we're talking about here is the idea that we're hitting either a quark or a gluon, something inside the proton, where the likelihood of me hitting it is pretty much constant, or has a behavior that looks like an inverse square behavior, like the way that you would hit. If the Earth was infinitely small and you were scattering comets off the Earth's gravitational field, which is inverse square, you'd see this sort of behavior as well, this flat behavior just here. So that's the evidence that the stuff inside the proton is point-like, and that's the evidence for the quark parton model, best evidence for the quark parton model, this association with quarks and partons. But look, if there were just 3 quarks inside the proton and nothing else, and they all had the same mass, you'd see nothing here at all, except for at x equals 0.33. And in fact, this is a logarithmic scale, look here, the amount of stuff you see. So the number of things you see here is a factor of 10 more per decade. Nearly everything you see is up here at very low Bjorken x's. You see very little. You have to make a cut on the data to see the very hard scatterings. But most of your scattering is with a big soggy blob. Only occasionally do you have a hard scatter with a proton when you hit it with an electron or a muon. So, and it's 5 orders of magnitude, gentlemen, here. So 100,000 times more times you're hitting something which is just almost nothing, 3 zeros, 161, than you are down here hitting something which is supposedly your valence quark, which would have to be about 0.3. That's this one. It's not 5, it's 5 orders of magnitude down. You almost never see a quark, or a quark which carries the momentum of the proton. Oh dear. The thing looks a lot more complicated than the simple model of 3 quarks inside a bag. And it is a lot more complicated. And what's more, well, as you look harder and harder, this effect gets bigger and bigger. And actually, you can see further and further down here into what we used to call. Is it more complicated,
or is it actually showing that the quark model doesn't hold water because you're not seeing that 0.333 dominance?
it's not showing the quark model doesn't hold water, because the quark model isn't the whole thing because the quark model is an SU3 symmetry, special SU3 symmetry. The model, the field theoretic model of the strong interaction, quantum chromodynamics, also has an SU3 of color, and these things are gluons. So you could be hitting some of the glue that's sticking the thing together. Now, and
what's interesting, what strikes me as interesting about this is when you look at Viv's model, the 1/3, 1/9, 1/27, those resonance structures within the proton.
Yeah.
How does that jive with data?
I'll need to. I don't know. I haven't thought about it. So it doesn't jive because you're not seeing just scatterings at precisely these 3rds, 9ths, and 27th on the face of it. But it's more complicated than that, and this certainly fits in with both Viv and Mai's model of what these things really are, which is what you're really doing is you're scattering off a bit of a photon within the proton. So the actual numbers, no, and I'd need to think about it, and we need to get Viv answering that too. At least not at first sight, not looking at this piece of data anyway. But does it disprove the quark model? It disproves the simple quark parton model, yes, but it doesn't disprove the quark model as modified into quantum chromodynamics, no. But that model is not disprovable, as I said. So it's never going to disprove it. It should be able to, but it can't. It's never going to be capable of doing that because the model is too floppy. The model doesn't give, you can't calculate.
So it'll just be obviated is the point at a certain point.
Well, it just doesn't really mean anything making a comparison with the model. You can get the model. The model doesn't fit stuff a priori. It has a bunch of free parameters which you fit to this data, but it has about 50. So you can fit anything with that model, pretty much, nearly everything. So and it is just a model. It's not a theory. It's not a, you don't have an equation which gives you a number. You don't have something which you can calculate. You have something which is floppy at the extent that it has a bunch of free parameters which you have to determine from experiment. Unfortunately, it has more parameters to determine from experiments than there are experiments. So you're never going to pin it down. It's unpinnable.
It occurred to me as well that in Viv's model, the charge distribution of the proton is more equatorial, not spherical. I wonder if that different orientation has any bearing on this data.
Viv is looking at where people should be looking. He's looking at data at the kind of level where you begin to look at the structure at far lower energies. I mean, Viv's one with it all down here in Q². They're all off the left-hand side of the scale here. There's nothing there at all on this graph for the Viv stuff. You're talking about far lower energies. You're looking at 10 to the minus 15 meters. This is 10 to the minus 18 meters up here. This Q² also is a length scale. So yeah, it's the momentum squared of the scattered photon. So it's not a length scale per se, but it's related to a length scale.
I'm sorry, Viv's not here for this conversation.
He'll get the recording, thankfully. So the thing is, coming back to Pete's original question here about quarks, does my model support the quark model? Yes, it gives the symmetry of the quarks. It gives the reason for the existence of all of those, for the SU3 symmetry of the quarks as being something which is geometrical, which isn't simply imposed as being something that you measured by having a look at a pattern. It comes from the dimensionality of the underlying rotations that are effectively 3 left rotations, are rotations that fit together. Remember, we talked about a fundamental rotation being x to y. Well, you can mimic that by going 3/4 of the way around. If you're going round leftwards, so if you're going from x to y, which is an anti-clockwise rotation, you can get to a rightwards by doing a single rightwards rotation, but you can also get equally to a right rotation by doing 3 lefts, by doing 3 unit rotations. Those 3 unit rotation objects give you the quark model, as is now in one of the videos which have been posted on Quicycle. So yes, it does do that. It does do the quark model part of it. but it doesn't give quarks as separate particles. And the evidence doesn't support the idea that the proton or neutron are simply composed of three hard objects carrying most of the momentum of the proton. And as you look harder and harder, you see it less and less. Not only that, the vast majority of collisions that you see are not with something which looks like a proton constituent with a sixth or a third of the proton mass, simply. And there's the evidence in front of you, measured at CERN and recent. So there you go. I'll stop presenting now. Can you stop this one for a bit?